Hello everybody, this is Dr. Mohuya Chakraborty delivering lecture on information theory. In the last lecture, we have learned about the different communication channels. We talked about binary symmetric channel, binary asymmetric channel and solved some of the problems. Today we are going to study about the channel capacity of discrete memoryless channel. If you recall, there are different types of channels. Some channels are discrete and some channels are continuous. Now what are discrete channels? A discrete channel is a channel which can support passage of discrete type of information, as I have already explained. And continuous channels are channels which can transmit continuous type of information. Now let us see in this lecture what is the channel capacity of discrete memoryless channel. Let us consider a source X having a number of symbols x1, x2 up to xr, and we consider a destination y having symbols y1, y2 up to ys. Now yk will be equal to xk only when there is no noise. That means no change in the received signal as per transmitted signal. Now in the presence of noise, as is actually the case for all practical situations, yk will not be equal to xk. So a certain amount of uncertainty there arises regarding xi when yj is received in the presence of noise. Let us consider pxi/yj to be the conditional probability that xi was transmitted when yj is received. Then what is the uncertainty about xi when yj is received? As per my previous lecture, we have to find here the information content, that is the uncertainty in the transmission of the signal, and that is given as log of 1 by probability. Here what is the probability? Probability is the conditional probability xi/yj. So the uncertainty in the transmission of xi when yj is transmitted is given as log of 1 by p of xi/yj. Now if we average this uncertainty over all the xi's and yj, we get h of x/y, and as per previous discussion, h of x was the entropy of the source x. Now h of x/y gives the entropy or uncertainty about x when yj is received. So this is the uncertainty or the noise. So we can write h of x/y to be equal to double summation ij p of x comma yj. This p of x comma yj is the joint probability of xi and yj times log of 1 by conditional probability p of xi/yj. Let us keep it as equation 1. Now if we consider a noiseless channel, then if we think that p of xi/yj is equal to 1, that means true. xi/yj is true means xi is transmitted when yj is received. Then if you look at the right hand side of the equation 1, we get it as 0. Because if p of xi/yj is 1, then log of that thing will be equal to 0. So the right hand side of equation 1 will be 0. Again, if p of xi/yj is 0, that means it's not true. Then also, as per the probability equation, p of xi/yj is given as p of yj times p of xi/yj, and that is also equal to 0. So we can conclude for both the cases, when p of xi/yj is 0 or 1, equation 1 tends to 0. So we can say in the absence of noise, h of x/y will be equal to 0. That means there will be no uncertainty in the transmission of signal x when yj will be received. This uncertainty actually is the average loss of information about a transmitted symbol when a symbol is received as it is caused by noise. Hence we can write h of x/y is the equivocation of x with respect to y. Similarly, by using Bayes' rule or Bayes' theorem, we can write P of xi slash yj to be equal to P of xi upon P of yj times P of yj slash xi. This P of yj slash xi is the conditional probability that yj is received when xi is transmitted. This goes as equation 2. Now, on simplification, we can get simultaneously the equations 3 and 4. So, equation 3 gives P of yj slash xi times P of xi as in equation 2 upon summation of I P of xi comma yj. And ultimately, we arrive at equation 4, which gives us the value of P of xi slash yj. Now, what is Bayes' rule? You see, in probability theory or in statistics, Bayes' rule actually it describes the probability that an event will occur based on the prior knowledge of conditions that may be related to the event. Let's say, for example, if we consider that cancer is related to a person's age, then if we use Bayes' theorem, a person's age can be used to more accurately access the probability that he or she has cancer. This is much more as compared to the assessment of the probability that the person is having cancer without the prior knowledge of the age. So that this is the general rule of Bayes' theorem. This can be used in our case too. Now we go to mutual information. We have seen for noise free channel, h of x is the average information per symbol, because in this case h of x slash y or the equivocation is equal to 0. But this h of x slash y is the uncertainty or the noise that we invoke when we are passing the signal. So the amount of information that is received on an average is not only I of x, but it is the joint information of x and y, where x is the transmitted symbol and y is the received symbol. So we can write according to equation 5, I of x y bits per symbol is given as h of x minus of h of x slash y. This minus h of x slash y is the uncertainty when it arises due to the presence of noise. So this I of x y is called the mutual information of x and y, because here we are considering the noise also. Previously we talked about the information of ix when we considered only the probability of transmission of x and what is the information content when we transmit x. Now we have to consider the noise and we have to think what is the probability that we have transmitted x and we are receiving y. So that is the reason we are telling equation 5 as mutual information of x and y. So if we put the value now in the previous equation, we can write I of x y, which is the mutual information. As per previous definition, it is p log of 1 by p. So here p will be p of xi, because we are transmitting xi, the probability of xi multiplied by log of 1 by pxi. Now this minus h of xy, which is the equivocation, so we put the value of equivocation and write it as double summation ij p of xi comma yj log of 1 by p of xi slash yj. This p of xi slash yj is the conditional probability of the transmitted symbol xi when yj is received. Now looking into the channel capacity of discrete memoryless channels, we know from the theory of probability summation of p of xi yj, which is a joint probability, is actually the probability that xi has been transmitted. So if you put these values in the previous equation, we can get, after a series of reduction, we can ultimately get equation 7 as ixy, which is the mutual information of x with respect to y, as double summation ij p of xi yj log of p of xi yj by p of xi p of yj. So this goes as equation 7. Alternatively, you can use also Bayes' rule, and if we put it in equation 6, we can get it as I of xy is given as double summation ij p of xi yj log of p of xi by yj by p of yj. This goes as equation 8. Now we can substitute equation 4 into equation 6 and ultimately we can get equation 10 as I of x comma y will be equal to I of y comma x, because this is symmetrical in nature. So equation 11 will give us h of y minus h of y slash x is actually the mutual information of x and y. So we can ultimately conclude that I of x y is actually given as ix hx minus h of x slash y, or hy minus h of y by x. Now here we can find some useful information, as we have already discussed that h of y slash x is the equivocation of y with respect to x, and this gives the average uncertainty about the received signal or the symbol when the transmitted symbol is known. So we can use equation 11 and rewrite it as equation 12. We can get, as I have already told you, h of x minus h of x by y is equal to h of y minus h of y by x. This is nothing but the mutual information I of x comma y. This I of xy will be maximum, for some set of probability p of xi, and this is called the channel capacity. So you see, look at equation 13 where we have written Cs, which is the maximum channel capacity for the probability of some values of xi, and that is given as maximum of I of xy, which is given in bits per symbol. Now from this discussion we have, let us come to some of the observations. Observation number 1, we can see, since we know that information is always greater than 0, greater than equal to 0, so we can conclude that h of x should always be greater than equal to h of x by y. What is the meaning of this? The entropy of the source should never be less than the loss of information, loss of uncertainty. Okay, so h of x should always be greater than h of x by y. If this is not true, then information I of xy should be less than 0, which is not true. Observation number 2, we can see, if I of xy is 0, that means there is no information content, then we can conclude h of x will be equal to h of x by y. What does that mean? That means that x and y are statistically independent in nature. Let us look at observation 3. Since h of x slash y is the conditional self-information about x given y, and h of x is the average uncertainty, or we can call it the self-information of x, then I of xy, which is a average mutual information, that can be also called as average uncertainty about x having observed y. And looking at the last observation, we can find, since hx is always greater than equal to hx by y, the observation of y, you see, does not increase the entropy. When we are observing y, it is actually not increasing the entropy, it can only decrease it. That is, observing y cannot reduce the information about x, it can only add to more information. So this is all about the channel capacity of discrete memoryless channel. In the next lecture, we are going to look into the channel capacity of continuous channel. Thank you.